other cases are more complicated. So you really need, you may find also more than one solution. So you really need to check where is the maximum. And so let me make another graph to better discuss this. Let's suppose, once again, in order to be able to make this graph easily, let's suppose that we have only one decision variable, and I can plot the benefit depending on the decision variable. And let's suppose that the domain for the decision variable is between 0 and x star. Let's suppose that this is a water allocation and we cannot exceed x star. So let me show you what may happen. And let me make a very simple example. Let's suppose that you have a benefit function like this one. So, how many solutions would you find in this case? You would find 1, 2, 3, 4 solutions. Two maximum and two minimums. Among the two maximum, one is relative, this is relative, and this is absolute. So basically you have to compute the benefit for each of the solutions and to identify the highest benefit. So you have to check that your solution is not a minimum, you have to check that your solution is not a relative maximum. This is the second check. Again, you have to check that your solution is not a minimum, and you have to check that your solution is not a relative maximum. And then there is a third check that you need to make. This is the check that the students have more difficulty in understanding. And I think this graph clarifies the situation. You see that the maximum here is not given the maximum benefit by any of these solutions. The maximum is here. And this is a maximum that you wouldn't find with the method of the Lagrange multipliers. Why is that? Because the method of the Lagrange multiplier tells you where the analytical function reaches a maximum. In this case, the maximum is not an analytical maximum. It's given by the fact that the benefit function reaches the boundary of the domain. And there is no other way to see this maximum but computing the benefit for the boundary conditions. So the check is simple. You compute the net benefit for x equal to x star, and you check that the maximum that you previously identified is higher. If not, then you take as maximum value the boundary condition. And you see here you have two boundary conditions, x equal to 0 and x equal to x star. Keep in mind that in water resources management you could have the maximum benefit for allocation equal to 0 because you have costs. And in some cases you may find that the costs are always higher than the benefits. And this means the costs are always higher than the gross income, let me say. And this means that there is no physical solution. The solution is allocation 0. The solution is not making the plant that you are designing. And therefore you must check the boundary condition for x equal to 0. So in this case you have two boundary conditions, and it's very simple, as you see, to check them. You just need to compute the benefit by giving to x the value that corresponds to the boundary condition, so it's very simple. But if you have two decision variables, be careful, because the boundary condition grow exponentially. Because for two decision variables, you don't have four boundary conditions. You have to explore all the possible combinations. So it's minimum, minimum, maximum, maximum for two decision variables, I mean, and then minimum, maximum, and maximum, minimum. So you have to explore all the possible combinations. So it becomes a bit more complicated. Okay. So basically for the equality constraints we are done. And also, you know, because you explored it at the beginning, how to solve the problem if you don't have constraints. Okay, so basically you know how to solve the problem analytically if you don't have constraints and if you have equality constraints. Now let me move to inequality constraints. And inequality constraints are given by, let me delete the blackboard. So, I use the brown chalk. I hope you can see it. If you have problem in seeing it, just let me know and I go to the reception to take a white one. Can you see it? Okay? So the inequality constraint typically is a constraint like that. And it's the most frequent constraint that you find in water resources management. The sum of the allocation should not exceed water availability. Okay, so how can we deal with it? And let's suppose that we have a net benefit function as usual. So let's write now the Lagrangian in this way. Lagrangian x lambda, and I left some space here because I need to introduce an additional variable. I will explain to you why. It's given by the net benefit, x, minus lambda, which multiplies something. In the previous version, we had here the constraint, the equality constraint. And therefore, we had x1 plus x2 plus x3 minus q, but this is an equality constraint. So, how can we solve then the problem of transforming this constraint that we used before in inequality constraint? First of all, let me say that there is a trick that we can use to transform this inequality constraint in an equality constraint. What is the trick? The trick is to introduce an additional variable, so that I can write the constraint in this way: x1 plus x2 plus x3 plus s squared is equal to q, where s is variable. So, first of all, what is s? It's a dummy variable. Why it's squared? Because I need to make it positive. Because the inequality is lower or equal. So you see now that for varying s, you explore all the possible solutions that meet the inequality from which I started. If s is 0, I go back to the equality constraint. If s is whatever value different from 0, then it's squared, and then I explore the solution whose sum is lower than q. Okay, basically, what I should do is just add plus s squared here and add s here. Okay. Now, of course, I already understand that to get the solution of this problem, I have to take the partial derivative of the Lagrangian as I did before, but there is one more partial derivative. And let me say that the first, or the old, let me say this, the old partial derivative don't change. Because when you compute the partial derivative with respect to x, it doesn't matter if you added s squared here. I mean, if you take the partial derivative with respect to x, the fact that you have one more variable here which doesn't depend on x means that your partial derivative doesn't change. So the partial derivative with respect to x don't change. They are the same as before. What changes is the partial derivative with respect to lambda, which becomes like this. But it's a trivial change. It just gives back the constraint. So you just have back your constraint. But I have one more partial derivative of the Lagrangian. Sorry, I forgot here a s. Okay, Lagrangian depends on s. With respect to s. So now we have the partial derivative of the Lagrangian with respect to s, which is minus 2 lambda s, which is equal to 0. Now, there are two possible solutions to this last partial derivative. And the two possible solutions are lambda equal to 0 and s equal to 0. What does this mean? Okay, let's discuss it. So basically, we got two subcases. One case is s equal to 0. What does it mean? It means that I am going back to the equality constraint. So, to explore what are the possible x value that correspond to s equal to 0, I just have to go back to the previous solutions. I just have to consider the constraint as an equality constraint and I find my solutions. I find x values that correspond to s equal to 0. These are possible solutions of my problem, because they correspond again to one of the two cases, s equal to 0. So let me keep these solutions in memory, okay? And now let me move to the second case. The second case is lambda equal to 0. What does it mean, lambda equal to 0? It means no constraint. Again, it means no constraint. So what should you do to explore the solution for this case? You should just remove the constraint and find the solutions. You know how to do that. And keep in mind that this is straightforward. It's by intuition. You can understand that the solution is smart. If you have an inequality constraint of this kind, basically what I'm proposing to you is to split it in two problems. One problem is, let's remove the constraint because it corresponds to the minor. If the allocation is minor, is less than Q, you don't need your constraint. So let's remove it. The second sub-problem is the equality. So you can split a minor equal between minor, remove the constraint, and equal. Use the equality constraint. And each of these two cases will give you solutions. Possible solutions. You have to find the best one. The solution that gives to you the highest benefit. So you just compute the benefit for each of them by including the boundary conditions, by making the checks that I mentioned to you before, and you keep the highest benefit. You keep the solution that leads you to the highest benefit. So, as I said, it's a very smart solution. You have an inequality constraint, minor, equal. You first consider the minor, no constraint, and then you consider the equal, equality constraint. You get solution and you find the best one. Keep in mind that when you remove the constraint, you must check that the solution that you find give you an allocation that is lower than Q, because by removing the constraint, you would find also possible solutions that lead you to allocate more water than Q, and therefore you have to reject them. Okay, so basically, with the Lagrange multiplier we are done. I hope that you understood them. And, you know, it's a topic that is not straightforward, basically, because analytically, from an analytical point of view, the development is a bit complicated. But if you look at the essence and the physical meaning, it's quite easy to understand. And this is an analytical method. Analytical methods, I mentioned to you at the beginning of these lectures, that are not really much used today as they were in the past. And let's see why. Let's discuss a little bit it. First of all, I think, what are the advantages of analytical methods? There are two advantages. The first is that the computational resources are limited. They are very computationally cheap, and the second advantage is that you find an exact solution. These are the two advantages. What is the disadvantage? It is, what is the disadvantage of the Lagrange multipliers method? And let me discuss two disadvantages. The first one is that you need to take the derivative of a benefit function and a constraint. Or let me say a benefit function. The constraint is trivial. So you have to take the derivative, an analytical derivative of a benefit function. And in some cases, your benefit function could not lend itself to an easy computation of the derivative. Or the derivative cannot be computed. So there are benefit functions for which you cannot compute the analytical derivative. You need to use a numerical computation. This is a huge disadvantage. This is a huge disadvantage because if you have to compute a derivative by using a numerical approximation, then the advantage of using the analytical solution vanishes. The numerical computation of the derivative is computer intensive and it's not exact. So the fact that in some cases you cannot compute the derivative analytically is a huge disadvantage. So this is the first one. We need to compute a derivative, to take a derivative, and in some cases it is not possible or it's very difficult. This is the first one. Second disadvantage, when you get a lot of constraints and a lot of decision variables, the method becomes much complicated, a lot. Because you see that any constraint requires an additional variable, lambda. And if the constraint is an inequality, any constraint requires two additional variables. So let's think of a situation where you have four constraints and they are inequality constraints. Then you get into a mess because it means that actually you have to solve two problems, and one problem is with four constraints, and this means that you have to use four lambdas. You know, your computation becomes complicated, and when you have a lot of decision variables, I already told you that checking the boundary condition becomes complicated. So at the end of the story, this method, if you have a lot of constraints and a lot of decision variables, becomes messy. This is the second disadvantage. And at this point, you may ask me, what is the alternative then? The alternative is very straightforward today, because it's just to move forward by simulation, which means by chance. So the alternative that I'm discussing now, and before I start, let me say two things. First, the inequality constraints are not in my slides, so just keep it in mind. It's a part that is not included. And also the simulation methods, now I'm teaching them by just providing a discussion. It's very descriptive. And therefore, I didn't put any slide on my website for this. But as you will see, for the simulation method, it's just a discussion. There is nothing that you really have to study. There is something to learn, but you learn with this discussion. And let me introduce the simulation methods by making a very simple example. Let's suppose that you have a benefit function, MB, which depends on one decision variable only, MB x1. And let's suppose that x1 must be lower than 10. What is x1? Let's suppose that it's a water allocation, and you know, one possibility that you may think of is to find the best value by chance. So by simulation, by trial and error. And one may say, okay, this is a problem because you know, I have infinite solutions. I have x1 is a real variable. I have infinite values that I should try. But this is indeed not true. They are not infinite, because when you are talking about water allocation, basically you can discretize the variable depending on the number of digits that you need. So depending on the level of detail that you need, usually when you speak of water allocation and your range is between 0 and let me say 20 liters per second, you don't need to tell your users that you are allocating like 5 and 4, 6, 7, 8, 9, 1. He's not interested in all these digits. Usually, once that you limit yourself to the first digit for liters per second, it's really too much. So basically, you don't have, if your constraint is x1 lower than 10, you just need to try 100 values, and that's fine. So instead of taking the derivative of this function, instead of equating the derivative to 0 and computing the solution, why not computing 100 times the benefit with the PC in R? It's very simple, and then take the x1 value that gives the maximum. So this is much simpler. Of course, this couldn't be done 20 years ago. And now it's possible, because with the PC, this is very easy. And you may, like in Excel, for instance, you may just, in a column, write trial values of x1, and in the adjacent column, you compute the benefit, and then you just have to start from 0, and then 0.1, 0.2, until 10.0. These are 100 values. And then you compute your benefit. And then here, you compute the max of the ND. In Excel, you have the function max. You identify the maximum and the corresponding allocation. It's very simple. And also writing 100 times the benefit function is straightforward because you use the copy function of Excel. And in R, you will make a loop. It's something that takes no more than 1 minute. If most of the time it's just to write the net benefit function if it is complicated. But once that you wrote it in R once, that's it. And basically, this is what it's done today. Because it's true that it's computationally intensive with respect to the Lagrange multipliers. This is much more computationally intensive. And you wouldn't do that if you had to compute on a paper. But now, the fact that the computational resources are not a problem. And the fact that you don't find an exact solution, as I said, from a practical point of view, it's not a problem because your users don't need so many digits. And even if they needed the second digit, okay, let's make 1,000 computations, no problem. So these simulation methods are today more and more applied, and I would say that they are the solution that is applied today. And I tell you that sometimes I wonder whether it's the case to continue teaching Lagrange multiplier to students, because in practice you will never use them. I think it is anyway useful because you know, when you have an opportunity to find an analytical solution, I think that you should know this opportunity. Because the analytical solution is, from a physical point of view, is something that is much more understandable, and from a theoretical point of view, you have a solid basis which you should know. So this is why I'm keeping teaching this. But from a practical point of view, this is the solution that is used today, which is not problem-free. Why is that? Because of course, I told you, no problem in doing that, okay? But let's suppose that the decision variables are 2. Now, it becomes a bit more complicated, because if you have x1 and x2, and x2, you have 2, and the constraint is x1 plus x2 minor equal than 10, you see that the combination that you have to try increase a lot. So So basically, with two variables it's still manageable. Because basically what you do here, you know, if it's an equality constraint, it is easy to manage. You fix one and the second one is computed through the constraint. But if you have an inequality, it's a bit of a problem. So it becomes, the number of solutions increases. If you have 10 decision variables, it becomes almost impossible to manage all the possible solutions. So what I usually do, if I have just two variables, what I usually do is to pick them by chance. So basically what I do is, let's suppose that this situation, I ask the computer to generate x1 in the range 0, 10. This is a generation. It means that I ask the computer to, by chance, extract x1 in the range 0, 10. Let's suppose that I get 5 times 2. Then I still have left 4.8 available that I can assign to x2. So I make a generation in the range 0, 4.8. And then let's suppose that I get 2 plus 8. It's one trial. So I found one trial by chance, and then I compute the benefit. And then I make another trial. And so on. You see that I'm not exploring all the possible solutions. I am exploring the space of the solutions by chance. So if I identify the space of the solutions as a region, I am just picking up points by chance in this region. And of course I may pick up the same solution twice. So I'm not exploring the whole space like I did before when I had only one variable. I am exploring the space by chance. But of course, if you perform 1 million trials, you are reasonably sure that you covered, with a good coverage, the whole domain. This is what is done via simulation. Still, you know, if the decision variables are many, it becomes a bit complicated because you have to perform a lot of simulation, and then it's easy with two. It was easy for me to explain to you an algorithm for getting the trial solutions. But if the decision variables increase, then the algorithm becomes, you know, difficult to manage. It becomes a problem which is an IT problem. It becomes a programming problem. And if IT is information technology, probably you know better than me. And it becomes a programming problem, not a mathematical problem. It becomes a problem for software engineers to find a good algorithm to explore this space in an efficient manner. Because otherwise, if your algorithm is wrong, you risk to explore only subregions of the space. And also let me say that if you keep moving forward by chance, and you have many decision variables, you may need millions or billions of simulations to cover the whole space, and this may become a problem. Even with modern computational resources, if you start performing billions of simulations, it may require time and may become unfeasible. And therefore people started to use computers in parallel, because otherwise the computing time was too long. And still today, some people that use these techniques in water resources management, they use parallel computing because they need a lot of computational resources. And so this became a problem because, you know, parallel computing is not so easy. It's, from the point of view of information technology, when you have to put together the results, you know, it's not easy because you have different computers performing different parts of the computation, and then you have to put them together. And again, it becomes difficult. And therefore, people started to make effort on the algorithms in order to perform a search that is not done by chance, but they devised driven search. So basically, let's suppose that you have a benefit function like this one. Again, one decision variable only, x and dx. And let's suppose that your range is between 0 and x star. And let's suppose that the benefit function is done like this. So if you explore by chance, then you explore the whole space. But people have the idea of performing a driven search, like instead of moving forward by chance, you start exploring the space with selected points, making a discrete exploration. And then you realize that the maximum is around here. And then you concentrate your search here. So basically, then you hit other points here, and then you realize that your maximum is here, and then you hit other points here.